continuation of that. Welcome back. So we'll continue that taper bar for a circular cross section. So as we know, the D1 is in a smaller diameter and the D2 is in a larger diameter, where the D is the diameter of that particular end, where the L is the length of the bar. So now we have discussed about the cross sectional area. Now we got pi into pi by 4 into d square, that is normal. So where we have considered the k, that is k is nothing but the difference between larger end minus smaller end divided by length. Now similarly, to find the axial stress at that particular end x, the x is nothing but the distance from point A, where load by area, that is what we normally the stress what we calculate is load by area. Now for the axial stress, by multiplying this, P is nothing but a load, where 4 into P, that is I am cross multiplying that particular area. Now I am shifting this 4 to the top. Now area is nothing but pi into d1 plus k into x whole square. Now this is an axial stress at this particular condition. Next is nothing but a change in length. So change in length is nothing but an dx. Dx is nothing but a change in length from a smaller diameter to the larger diameter. So that change in length we are going to define in the form of delta. Delta indicates nothing but delta L or delta D means delta indicates means that is change in length or change in diameter. So that is the reason we are going to use the symbol delta. So now for that change in the length is nothing but original length, that is what we required is stress. Axial stress what we got is sigma x into dx. Dx is nothing but a change in diameter divided by E. E is nothing but a Young's modulus, or what we call it as an change in that is length, or what we call it as an Young's modulus E. So now by multiplying this, 4P is nothing but a load, where for the shear stress same equation I have written, and we have added that we have multiplied with the strain, or sorry, we have multiplied with the Young's modulus. So now the total change in length, we need to identify what is the total change in length whenever the diameter is varying from smaller end to the larger end. Now by integrating that 0 to L, 4, that is P into 4, P is nothing but a load with the dx is the change of diameter, where pi into E into d1, that is what we got from the equation from the area and the stresses. Now by rearranging the terms, what we got is, now after rearranging, minus 4P by pi into E into K, that is now I have taken these terms to the 1 multiplied with the 1, that is by integrating terms 0 to L. Now by substituting that limits of integration limits, that is 0 to L, so we got an equation that is 4P by pi K. Now again by rearranging these terms, we got an 4P by pi into Ek, that is in the brackets 1 by d1 minus 1 by d1 plus k into L. So L is nothing, k is nothing but the difference between d1 minus d2. But d1 plus KL will be equal to d1 plus d2 minus d1 divided by L into L. That will be equal to d1 will be equal to d2. Now by substituting all these equations, by substituting these above equations, finally I need to find out what would be the change in length of this particular taper bar. So now with the above this substitution, change in length, that is 4P by pi into Ek will be equal to 1 by d1 minus 1 by d2, that is will be equal to 4P will be equal to pi Ek into d2 minus d1 by divided by d1 into d2, where by substituting the k. So the k value is nothing but d2 minus d1 by L in the above expression what we got in the elongation. Now finally for the taper, the circular section of the bar can be obtained, that is total change in length is nothing but a change in length will be equal to, you can able to see that 4 P is nothing but a load and L is nothing but a length, and pi E is nothing but an Young's modulus, where D1 is the smaller diameter and the D2 is the larger diameter with respect to this total change in length. So now we can able to see this in this particular diagram, where the X is total length, where you can able to see the whenever the load is applying. So what would be the total change in length is nothing but by using this equation we can able to identify the change in length in this particular tapered cross sectional bars along with the tapered bars of circular cross sectional. So based on mainly this type of equation used to find out the change in length, that is change in length nothing but to find out the change in length nothing but finding the strain. So this is how we got an equation. By using this equation we can able to identify the change in length in that particularly tapered cross sectional bar. So next one is about the elongation of tapering bars for rectangular cross section. So now we have seen for a circular cross section. Next we are going to see for the rectangular cross section. So similarly you can able to see the diagram where the length and where you considering a bar of same thickness T throughout its length, tapering uniformly from the width, that is the width B, what we taken B, and the one end of the width breadth B and the other end over an axial length. You can able to see the width of this area is small and it is the other end is the B, where the small b and the capital B. We are going to see, and both at the both ends of both the tensile load is applying at the both ends, even at the small end and the larger end, and the T is nothing but a thickness of the particular tapering bar. The thickness will be same throughout this particular material. So on L, now we are going to see that. So since the width of the bar is continuously changing, the elongation of the first computed over an elementary length, then the integrated over the entire length. So by considering an elementary strip of that width bx and the length dx at the distance of x from left end. So you can able to see this. So we are going to consider the width from the left end, that is from the small b to the difference is what we call as an x. So by using the principle of similar triangles, the following bx can be obtained. By using the simpler triangles, now by using this equation, we are going to derive that equation, or we can able to obtain that particular equation. So where bx is nothing but b is a smaller end and the capital B is nothing but a larger end of the tapering bar, and L is nothing but a length, and x is nothing but a change in, that is a length from small end to the B. Where similarly k is nothing but width from the larger end to the width from smaller end divided by length L. So it is similarly like in a cross sectional area, but only the notations is going to takes place changes here. So now the cross sectional, again the cross sectional is, so here pi by 4 into d square, where we have any diameter there we can able to consider. So here we don't have any diameter, so with respect to, instead of diameter we will be having a thickness here. So we are going to consider the, instead of diameter we are going to consider the thickness, that is b is nothing but a smaller end tapering end, and the Ka is nothing but the difference between the small end and the larger end with respect to length, and the T is nothing but a thickness. Now for similarly axial stress, so sigma x is nothing but load by area. Now area is, load is similar P or F, you can get area is nothing but B plus Kx into T with respect to the diameter. We don't have diameter, so I am going to consider with respect to the thickness. So next, change in length over, that is change in, now I need to find out the change in length, that is dx. So dx is nothing but an axial stress into the change in dimensions with respect to the Young's modulus. Now by multiplying this, so P into dx divided by Young's modulus into, that is area of cross sectional, what we got b plus kx into t. Now to find the total change in length, that is delta L, is by applying the limits 0 to L. So by equating that limits, we are going to get P by E into E is nothing but Young's modulus, thickness into K, K is nothing but a B minus B divided by L, that is from the larger end minus to the smaller end of the tapering bar divided by length. By substituting these limits, we are going to get sigma L, that is change in length, is nothing but load by Young's modulus into thickness into K with respect to limits of B and capital B and with respect to L. But B plus K will be equal to B, again capital B minus small b divided by L, so that will be equal to the larger end. By substituting above equations, now we can able to identify the equation, that is change in length for an rectangular bar, that is PL divided by E into T, that is capital B minus small b, the linear equation, that is B by B. This is what the equation we want to get for the whenever we are going to substitute the, or we need to find out the change in length for particularly considering this tapering bar for a rectangular cross section. So the equation what we got is change in length for a rectangular cross section is P by L by E into T by B minus B into B by B. So capital B is nothing but the width of a larger end, and the small b is nothing but the width of the smaller end, and P is the load, and L is nothing but the length, E is nothing but a Young's modulus of that particular rectangular cross section, and T is nothing but thickness. So this is the equation we need to remember, that is change in length. To find out whenever we are going to find the change in length in a rectangular cross sectional is about the equation, we need to remember this. So this is about the how we need to find out the equation in the rectangular cross sectional for a rectangular